Yeah, I apologize for the delay. Give my best to do this. Okay, so let us recall what we did last time. So last time we talked about toric varieties. So it is essentially a variety plus torus section. So we have some variety X, we have some algebraic torus. Acting on it in such a way that the variety X itself kind of contains the whole algebraic torus as a proper subset, and the action on this algebraic torus inside of X is usual multiplicative action. Action of T on T. So T is the group, so we can turn this group operation as an action of torus on itself. So T1, T2 goes T1 times T2. Yeah, and action on X should be T. Yes. T includes X. So the action on X is like multiplication by T, and on a proper subset, this multiplication by T is like a multiplication in this algebraic torus. Okay, so that was kind of formal definition. And then we started kind of with some simple examples. Examples like, okay, we can take algebraic torus itself. So it is a Lie group, so it is a manifold, and it is a variety. So then we can take kind of C. So we looked at C, we looked at kind of some Cartesian products. So if we have if C is toric variety, then Cartesian products of two copies of C is also a toric variety with kind of toric, with diagonal toric action. So kind of one interesting example is one-dimensional projective space CP1, when we need to kind of look at the toric action in two separate charts and see that the toric action, which is multiplicative, agree with kind of transition map that is also some kind of homogeneous transformation that goes to 1 over W. So then, from these simple examples, we went to kind of a construction for certain families of toric varieties. And then this construction was, so we discussed it as symplectic reduction. But there is a theorem that implies that if you perform a symplectic reduction of just kind of complex flat space like C, n plus s copies of complex numbers, molded by kind of U1 action that acts by some phases on these variables with some weights, and we perform this reduction at kind of regular value of a moment map. So we will get some variety x mu, which will be toric variety, and as long as mu is kind of nice interior point in the image of a moment map, so this variety would be independent on mu. So kind of this procedure of symplectic reduction is done in 2 steps. So on the first step, we kind of looking at kind of locus where moment map equals to mu, which we can denote as some kind of submanifold inside Cn plus S, which is G minus 1 of m. So that is kind of pre-image under moment map of this moment map value mu. And then we motion by, so we look at, we kind of take an ordinary quotient by a U1 action. So that naturally makes a dimension of this space x mu, like complex dimension, okay, real dimension of this space x mu will be what? Will be real dimension of Cn plus S, dimension of x mu, real dimension is what? Is real dimension of Cn plus S, which is 2 times n plus S. And then first we take a kind of submanifold inside of this x mu, just treat it as a real submanifold, and this real submanifold is defined by some collection of equations, and for our kind of action by phase multiplication, so these equations would be algebraic equations. So we have like some collection of equations, and the number of equations is precisely kind of real dimension of the kind of dual algebra. So when we impose G of moment map equal to some particular value, so we are kind of imposing the number of constraints equal to dimension to a dual algebra, and in this case, Lie algebra for U1 to the power S is just R to the power S, and dual algebra is also R to the power S. So that's why here we subtract S. So that will be like S constraints imposed by fixing the level of the moment. And then we subtract another kind of dimension now of our group. So here, for regular value of a moment map, this action is free and proper. So that's why the manifold we will get will be a smooth manifold whose dimension will be precisely a difference of dimensions of J minus 1 of mu and dimension of this Lie group. And in this Lie group has also dimension S. So therefore, here what we get 2n plus S minus S twice. So we get here real dimension 2n. So far, like here, we constructed a real manifold, and okay, symplectic reduction implies that it's real symplectic manifold. However, there is some theorem that tells us that symplectic reduction with kind of our group, which is very simple abelian group. So that is result of the symplectic reduction is isomorphic to kind of what is called GIT quotient. And this GIT quotient is essentially we take the same space Cn plus S. So then we subtract some fixed orbits, like some subsets of smaller dimension, and quotient it by kind of complexified group. So here the so the complexification of this group U1 will be C star. So here we perform like just ordinary quotient, but quotient of Cn plus S with some stuff removed by a cis direction to the power S, and kind of obvious reasons the dimension of this space. So this space, because it's a complex quotient, will be complex space, and its complex dimension will be exactly n plus S minus S. So dimension will be S. And the theorem basically tells that this GIT quotient is isomorphic to result of symplectic quotient. So I kind of prefer to talk about symplectic quotient rather than this GIT quotient, because in symplectic reduction, kind of sort of this procedure of removing extra stuff is sort of more straightforward, and easier. So here, kind of this extra stuff is essentially what we like roughly remove by using the model. However, here today I will briefly tell you how to kind of explicitly get the stuff that we remove, like how to get some kind of equations for this subvariety that we remove from Cn plus S to precisely get X. But we are not going to use this GIT quotient in our course, and even the symplectic reduction, we will kind of use it very rarely, and our key, so that is kind of construction 1. So, but our key construction to kind of practically describe toric varieties would be construction 2 with this kind of toric varieties from polytopes. Okay, so let me kind of start with several examples before I will kind of phrase a formal definition of these toric varieties from polytopes. So let me start with C. So as we discussed before, so if you look at complex numbers with say coordinate z, so then kind of one-dimensional torus is just a star. So the torus action would take this point with coordinate z to z times t. T is kind of non-zero complex number. Among points in C star, so we have two types of orbits for this point. So if v equals exactly to 0, so then kind of for all t in C star, so let me call it t upper script t. So it's kind of what happens to v coordinate after t action. So all kind of elements of C star, they preserve this point z equals 0. So and kind of 0 is orbit of C star, and furthermore it is kind of zero-dimensional orbit. So while if I take a complex number which is non-zero, so then multiplication by t kind of in principle can turn any non-zero complex number into any other non-zero complex number. So here, like kind of for any w which is non-zero, there exists some kind of t such that w is g times t. So when you fix it, we can reach any non-zero point by literally just dividing one non-zero number into another non-zero number to get the key group element that we need to kind of reach that point. So therefore here kind of orbit is star, and this orbit is kind of one-dimensional orbit, and that is kind of C star itself, and then it is kind of proper subset here. And so therefore we can describe structure of orbits on C. So C star orbits on C is kind of a union of two orbits. So it's kind of C star union point at 0. So therefore our toric variety C is a union of two C star orbits. Okay, and similarly we can analyze other examples. So the kind of more interesting example is CP1, which I often would just call P1. So in this situation, kind of inside of P1, we have like affine chart C, And in this affine chart, we also have. Okay, let me do it like this. So let me describe a point on P1 using homogeneous coordinates. So that are kind of parameterization for points on P1. So it's pair of complex numbers 0, 1, up to kind of overall multiplication by non-zero complex number. So now the action of C star in this homogeneous coordinates is kind of very simple. So it's, yeah, okay, so it's, let's say it's like this. So T is not times Z1. So then for this action, if we look into a chart where the Z1 is non-zero, so there is such chart which is chart inside of P1. So in this chart we can use a kind of coordinate Z0 over Z1, and in this chart we have a point which is in homogeneous coordinates like 0, 0.Z1. So and in this chart that is the point inside P1, and this direction preserves this point, and that is kind of the same as the point in origin that we had in C. However, in CP1 we can look at another chart. U0 is a chart where Z0 is not. So in this chart we can use a kind of this idea that we can simultaneously rescale Z0 and Z1 by any non-zero complex number. So we can rewrite a kind of equivalent form of this direction, which is kind of better adapted to the other chart. So we just kind of rescale this pair of complex numbers by t minus 1, which is a non-zero number from C star. So that is our torus action. So then in this chart we have another fixed point which is Z0.1 is also a fixed point of this direction. And then you can moreover prove that there are no other fixed points. So it means that for T1, and that all other points, like when we have, so all other points Z0, Z1, when both Z1 is 0 and Z0 is non-zero, so all these points, they actually, all the points taken up to overall scaling is actually C star, which is one-dimensional orbit. Okay. So therefore, the structure of orbits on P1 has the following orbits. So we have like simple one-dimensional orbit, which is this C star, which is isomorphic to this homogeneous points, where both Z1 is non-zero and Z0 is. So then we have two one-dimensional, like zero-dimensional orbit, which is, so it's the point at the origin. Let me kind of roughly call it Z equals 0 in this coordinates. The number coordinate Z0 over Z1. So this Z equals 0 in homogeneous coordinates is essentially Z0, 1. And Z0 is non-zero. So then, and there is yet another one-dimensional orbit, which is point at infinity. So to describe it, we actually need to go to a different chart when this point is infinity we define the point. So and not surprisingly that it just kind of point at 0 when we switch to Z0 and Z1. So therefore P1 is kind of a union of these three orbits of C star. And it turns out that it is kind of very convenient to depict the structure of these orbits using so we have depict orbit structure using certain polytopes. Let me kind of give you an example. So in the C star case, okay, so we have orbit which is C star. And for a C star orbit, we draw a kind of infinite line. So kind of C star orbit we depict on a polytope as kind of this non-compact real line. And essentially kind of how to see C star, how to kind of C star from this picture. So these orbits encoding should be kind of one-to-one correspondence. So we should be able to recover, and to recover C star, we need to kind of fiber a circle on top of this real line. So C star is kind of a circle, fiber it over R. So now, what if we have complex numbers? So for complex numbers, we have one orbit which is C star with this circle fiber over it. And then we add a kind of additional orbit. So that is kind of C star part. And then we add kind of at infinity of this real line, we add a point at infinity. And this point is just a point, so there is kind of nothing fibered or point fibered of it. And then to kind of restore our complex plane from this picture. So C star is kind of topologically a cylinder, so it's real line with a circle fiber at all. So to get from a cylinder to a plane, we need to kind of gradually shrink the circle to produce something like a cup. So this kind of animation of zero-dimensional orbit, it kind of adds a cup to the cylinder to turn a cupped cylinder into a plane. So similarly, in our example of CP1, so we have once again C star orbit with circles fiber over it. And then we kind of add the two cups at infinity. Okay, let me start using this radial coordinates. So this real line or this polytope happens in some radial coordinates, and we kind of compactify this real line which is 0 to plus infinity, not including the points at infinity. So we kind of formally compactify this real line to infinite interval by adding 2 points at infinity. While to see back CP1, which is topologically a sphere, so we need to kind of add these points in such a way that the corresponding circle shrink to 0 radius, and we get like a slicing of some kind of squashed sphere, slices into circles. Okay, so that was kind of a simple way of encoding, and this picture, when we ignore the circle part, so sort of kind of radial part of the picture, is what we call polytope. And it turns out that we can encode a huge family of toric varieties by kind of drawing certain polytopes and then assigning some kind of circle, or more general, if you have, say, two-dimensional, high-dimensional polytope, then we would have like a torus sitting over the middle point, and then as we approach various components of the boundary, so some of the circles on a torus would degenerate to a kind of lower dimensional tori, and we will kind of eventually get some. Okay, with compact polytope, we will get some nice compact tori. So now let me give you a formal definition of the toric variety from polytope. So definition. X is a compactification of C star to some power n by a polytope P. Okay, and this polytope P itself is kind of okay. Let me give it like this. So is an intersection, like finite intersection. Let me call it HB alpha from 1. Let me call it capital B. So it's finite intersection with the half spaces. So we choose kind of on Rn. We choose a vector B, and then for a vector B, we can construct a kind of hyperplane for which this vector is normal. So HB is a hyperplane with, okay, it should be inward pointing. Okay, so here not what is inward pointing. Okay, let's say the normal vector D. And then for this HB, we can define HB plus. So that will be HB plus. So HB plus is half space. With okay, so for a kind of hyperplane, there are two half spaces. And to distinguish them, we should tell whether vector B is kind of inward pointing or outward pointing. So this vector B being okay, so we have this half spaces, and then in order to get polytope, we intersect this half space. Okay, so that would give us this kind of picture that it will be some n-dimensional polytope that we get by intersection of certain number of this half plane. So in particular, if there are no half planes, then we just have Rn, and Rn just represents C star to the power n, which is okay non-compact. Okay, let me add to be more careful partial compactification. So to allow a situation when I have like smaller number of hyperplanes such that this polytope is not compact. So that's why it's partial compactification of C star to the power n, and in particular, if there are no these hyperplanes, okay, no compactification, it's just C star to the power n. So now the more interesting part is what to do with angular part. So over each point, okay, let's say each interior point So for this polytope, we have some boundary points and some interior points. So over each interior point, we have kind of, let me write it as 1 to the power n fibers. So here, over each point, we have kind of n-dimensional torus, n-dimensional real torus fitting over each point. So then, as we approach boundary, so for let's start with codimension 1 boundary. So codimension 1 boundary is kind of points lying on one of the hyperplanes. So codimension 1 boundary is kind of point on HP, or to be more precise, interior point on HP. So these HBs can intersect between themselves, so they would have like some boundary points. So let me just, like, if I have say 2 HBs, so let me take like a point somewhere here, which will be interior point on HB. And then for this interior point, for codimension 1 boundary point, we have S1 to the power n minus 1 fibers. But this S1 to the power n minus 1 is embedded into this high-dimensional torus by prescribing, or it is embedded by prescribing anyway, so to specify kind of n-1 dimensional torus inside of n-dimensional torus, so what we want to specify S1 minus 1 S. Okay, let me kind of write it temporarily like this. To specify n-1 dimensional torus inside of Tn, so is the same specifying kind of S1 that shrinks to a point. To a point as we approach the boundary point. So we kind of start at a point in a bulk, and we have n-dimensional torus sitting over this point, and then we gradually approach point on a boundary. So on top of point on the boundary, we should have n-1 dimensional torus, and therefore this torus should be somehow compatible with this approach, that we can still travel over smooth manifold, and this kind of specification, so S1 embedded into n-dimensional torus is characterized by its homology class. And homology class of S1 inside of n-dimensional torus is essentially collection let's call them M of n integer numbers. All this mk they're integer numbers. So to specify circle, we need to specify kind of windings of this circle over some basis in Tn. Okay, so therefore, kind of for each HP, we need to specify like some n-dimensional vector. Let's call it mn. So n-dimensional vector, integer valued, okay, m-dimensional integer valued vector, and it turned out that to kind of make this picture smooth and make this kind of construction of various story fiber over various kind of boundary components. So to make everything smoothly glue into kind of complex toric variety, we need to make a choice that the vector B is proportional to vector M. And furthermore, the proportionality coefficient should be integer, so this B should be some integer number k. Okay, non-zero integer number k multiplied by so therefore, in order to get a kind of smooth complex toric variety, we need to choose a very specific normal vectors in this radial complexification to polytope, and these normal vectors, they should be integer valued, and this kind of reason for being integer valued is because we also have like some circles and some tori fiber over different points, and we want these circles to kind of properly shrink to a point. So now we make an additional assumption. So that will be assumed for the rest of the course is that these vectors B are primitive. So primitive in the following sense that in kind of the collection of their components, B1 to Bn is just a collection of integer numbers, and we want these integer numbers to have no common divisors. So we want the greatest common divisor for all these numbers, B1 to Bn, to be just 1. So that's kind of additional assumption that will be enough to kind of describe interesting toric varieties with interesting mirrors. However, maybe later it would be interesting to see what happens if we relax this assumption. So that would lead to include some singular toric varieties. But for now, let us kind of simplify our life by requiring that there is no common factor in this normal way. Okay, so I think that finishes this definition. So once again, quickly recalling it. So X is kind of toric variety constructed from polytope P is kind of partial compactification of C star to the power n, such that we compactify radial part into some possibly infinite polytope given by intersection of hyperplanes. And the normal vector to these hyperplanes, they are integer valued vectors with kind of they're primitive integer valued vectors. And then to get a complex variety, we need to fiber a kind of tori of different dimensions, like over interior point of this polytope, we fiber n-dimensional torus. And then as we go to codimension 1 boundary, we shrink one circle, and this circle with homotopy class defined by this primitive integer normal vector. And then if you go to the higher codimensional boundary points, say here, like going to this point, which is intersection of a pair of hyperplanes like HB1 and HB2. So for this point we have like on top of this point we have S1 to the power n-2 fiber, and kind of the choice of these two circles that shrink to 0 are circles with homology classes B1 and B2. and you can extend this procedure to kind of arbitrary higher codimension boundary points. So codimension k boundary point would lie on intersection of k hyperplanes, and these k hyperplanes would define exactly k circles with integer with this kind of valid homology classes, because vectors are integer values, that will shrink to 0 on this codimension k boundary. Okay, so this construction is kind of okay. So the nice part about this construction is sort of easy to use, because what you do, you just pick up like some collection of integer vectors, like vectors b, and then just kind of intersect them, and the construction guarantees that you get some toric variety. So the disadvantage of this approach is that it's kind of hard to see what is the global structure of this thing, and it kind of generally it's sometimes tricky to recognize like some familiar toric variety on this picture. Okay. I think now maybe it's a good point to make a break, because the next thing which I'm going to talk is kind of how to go from this polytope picture to a symplectic reduction picture that we discussed last time. So in particular, we will see like how the polytopes emerge in symplectic reduction story, and how to relate, say, this collection. So here, the combinatorial data for our polytope, so some kind of polytope essentially is just a collection, that we call upper. It's just a collection of some integer valued primitive vectors, while in kind of symplectic reduction construction, the combinatorial data for this variety was essentially a collection of weight vectors. So here, for u1 to the s action, we have exactly s weight vectors in n plus n dimensional space. So these weights are also integers. So therefore here we have n plus s times s dimensional matrix for these weights. While here we have like so all these vectors, they are in n dimensional space, and we have a certain number b of this vector. So the data is n times capital B dimensional matrix with integer entries. And kind of natural question is kind of how to go from one combinatorial description to other combinatorial description. And that's what we're going to discuss after a short break. Let's make a 10-minute break. So, break. Before 11. I'll be back. Okay, so in the context, we will now talk how to relate these two approaches, construction of toric varieties by symplectic reduction and construction of toric varieties by describing a top or describing toric varieties complexification of partial computation of C star to the power n by lower dimensional orbits.
Excuse me.
Yes.
How can we see that B should be proportional to N?
So that we see from kind of having here local structure of a manifold as some kind of cup in n-dimensional space. So as we approach the boundary, the circle should shrink to zero, and so okay. Let me even give a simple example. So kind of local complex coordinates would be something like r plus I phi. So if you have like k coordinates like this, and then kind of going to approaching some boundary point means that we are going in some direction where r is kind of b times some large number. So we are going in the direction of vector b. So therefore, in order to kind of get the circle shrinking, so this kind of phi should be proportional to b over. Yeah, I think that's the best I can easily explain.
How can we identify this M vector as this M cycle as z to the power of M?
Yes.
Then what you want to show is this M is invariant at this hyperplane. The hyperplane is an orbit of this.
No, hyperplane is orbit of C star to the power n, but it's lower dimensional orbit. So
it's invariant under this M action.
No, why should be invariant? M is not defining action. So M are not weights of some action.
M is correspond to the S1, this cycle.
Yes,
S1.
but this S1 that shrinks.
So it means S1 act trivially on, or S1 is.
S1 should act trivially, so that should be a fixed point for. Okay, yeah. So we can treat these M's as. Yeah, maybe as the weights of S1 action inside of a torus, and we want this S1 action to be trivial. Yes. So that would mean that one of the circles shrink. Okay, so like in kind of local coordinates and in examples, that's sort of straightforward to see.
It means this S1 act trivially on this hyperplane, or it's the hyperplane is invariant in the S1.
No, S1 should act trivially.
Actually.
So the hyperplane is invariant on the rest of the torus. So it should be n-1 dimensional orbit. So rest of the toric action should kind of move the points on the hyperplane around. So
the action is like the mk's power of this ck to the power of mk.
Yes, which is kind of equivalent to shifting r by b lambda. So if I have like action with these weights, so we have like zk and let's call it t naught parameter for this one, and kind of on zk the action is like zk multiplied with t naught to the power mk. So if we go to radial coordinates, so it will be like rk plus mk log t naught, log absolute value of t naught, and so let's say let's say the t naught is some radial part and angular part. So then it will be mk r naught. So that is shifting rk by mk. And here we have phi k, and we shifting it by mk phi. Okay, so what we have? So for this, yeah, so this is hyperplanes, they're all at infinity. So here it's kind of the shift in the direction of mk sort of still preserves this hyperplane at infinity. But for faces,
you mean the hyperplane satisfy R? What's the definition of that hyperplane numerically?
So that was kind of R times equals lambda b, and we take this lambda b to infinity. So that kind of defined by hyperplane at infinity.
But why mk should be proportional to b?
Excuse me, I'm confused with the word shrink. I think it should be a quotient by a group, right? Quotient by some subgroup.
Okay, so shrink, yeah, okay, shrink near the hyperplane, yeah, and okay, on the hyperplane, yeah, I think it should be. Yeah, it should be quotient by S1 action with some weights. Yeah, I think it. Yeah, I agree. It should be quotient. Okay. Okay. I can't get like good explanation for why the weights should be proportional to vector B. So let me kind of keep it as my homework and return to it next time. Okay, so I will put the question here, and we will return to it next time.
So usually the question is why these two quotient is same?
Yeah, no. So here, like for torus part, we have a quotient, and for torus part, this weight should be integer. So that's the only way to kind of get a quotient to the torus of lower dimension, of one dimension lower. But then there should be an agreement between radial part and angular part. That it's kind of not two independent actions, but it was like a radial and angular part of a single C-star action. So in this C-star action, we kind of act on a radial coordinate by shift and act on a kind of angular coordinate by rotation. And the agreement of these two actions in the vicinity of hyperplane requires that this normal vector B is proportional to the vector M that defines a kind of circle over which we quotient n-dimensional torus. So and that was the question, like how to carefully see this condition from some local analysis near the hyperplane.
And for me, it seems that M and B should be perpendicular, because then it's like trivial, both in radial direction and angular direction.
No, it kind of no. M and B shouldn't be perpendicular because okay. So for radial action, so we have okay. So inside of C star to the power n, we have like our C star to the power n minus 1. And then this part of a C star should move points on a hyperplane around. So this thing should preserve hyperplane. So here kind of the non-compact part or radial part is r star to the power n minus 1. And in our coordinates, the action of this thing so here we have like some okay lambda alpha. So they are just weights of this action. So the action is this r plus kind of lambda alpha. Okay, I need to separate weights and parameters. Let me temporarily call parameters t alpha. So kind of for each element here is just some collection of weights lambda. So therefore here to preserve the hyperplane, so hyperplane is given by this equation equal to some infinite constant, but constant. So therefore to preserve this equation, we need to have a condition that kind of as we shift, this thing is 0. So this lambda b shouldn't change because lambda b is the position of this hyperplane. So that means that this lambda alpha, which are weights of a remaining C-star action, so they should be perpendicular to b. So the ones that kind of act on a hyperplane, so they are vectors perpendicular to b.
Why we consider the subgroup? We say the n-1 dimension torus as a subgroup of n-dimensional torus. But I think maybe we should think n minus 1 dimensional torus as a quotient of n dimensional torus. Because if we want to deform a fiber to a hyperplane, then we need to contract a torus. It's like we quotient a sample. So if we
Okay, but we can describe the subgroup as a kind of quotient group. So the subgroup generated by lambdas that are perpendicular to B, we can say that such lambdas, they are kind of general lambdas quotient by. Okay, so I wanted to quotient by lambda plus B, but that's not what. I want. Okay, so that is not quite the same. Yeah, so to construct a quotient, it seems that I need something like a unit, not unit, some vector with product with B being equal to 1. Okay, so let me not try to guess, let me kind of talk about it next.
Okay, so this n minus 1 torus is it act on this boundary.
Yes.
Okay, so what was this S1 act on the total manifold, and
Yes, so C star to the power n acts on the whole manifold, but it has orbits of a different dimension. So
yeah. So can you explain again what is this S1 inside this t to the power of n?
So here we have like orbit whose dimension is lower by 1. So it means that some subgroup inside of a torus kind of acts trivial on it. So that the action is kind of not a proper action. So it means that there is some kind of stabilizer subgroup that acts trivial.
Yeah, this S1 act trivially, but there are other n minus 1
Yeah, and then they act like
yeah.
like freely. So they move the points around. And kind of to specify this S1, we need to specify like some collection of integer numbers. Okay, so yeah, let me kind of explain the relation to this other construction. So for symplectic quotient, we have this weight W1 to Ws, and the moment map. It is kind of has moment map with image in S-dimensional space, so kind of Lie group of this dual Lie algebra of U1 group is R to the power S. So therefore here what we would have the following thing. So these weight vectors, they have components, let me call it capital A. So capital A runs from 1 to n plus s, so it's W capital A square. Sorry, dA absolute value square, and these weights, there are like s of them, and we will have a similar sums for all s weights. A from 1 to n plus s. So that is kind of a moment map that describes a map from C n plus s to a dual Lie algebra, which is R to the power s. Okay, and kind of to perform this quotient, we need to look at kind of G minus 1 of mu. So once again, let us describe mu in components. So mu1 to mu s. So mu is kind of s-dimensional vector, and therefore this j minus 1 of mu is kind of a locus where we have the following S equation satisfied. So W1 A, sum of A from 1 to n plus S, dA equation square. Let me call it alpha. Alpha runs from 1 to S. Okay, so now let me introduce different coordinates. So let me introduce the coordinates rho A that will be real valued and will be absolute value square of Z. So this rho A, so they are valued in kind of R bigger or equal to 0. Because the absolute value can take negative values. So let me describe this condition by saying that rho A are kind of real numbers, but with a condition that they are like real numbers bigger or equal to 0. And let me describe j minus 1 of mu in kind of this rho A coordinate. So then j minus 1 of mu is the following thing. So we have a collection of planes. So in rho A coordinates is just a collection of linear equations. 1 plus s equals a. So each of them defines a hyperplane in this R. Okay, so it's this condition, and then for all rho A's we ask it to be positive, and we consider rho A's to take real values. So that is kind of image of this j minus 1 of mu in this kind of radial coordinates. So in the radial coordinates, so first we take kind of a positive sector in this n-dimensional space given by this collection of inequalities that all rays are positive, and then we impose additionally S linear equations defined by weights of this U1H. So therefore, this j minus 1 mu geometrically j minus 1 mu is an intersection. We impose this condition simultaneously of n plus s half planes. So these half planes, they are defined by this equation. Rho A are positive, so it's n plus s equations, and as hyperplanes that are given by this linear equation. Alpha. So something which is given by intersection of half planes and hyperplanes. So that is by construction a polyton. And kind of the statement is that this polyton let me call it P with subscript W. So it's polytope constructed from weights. So polytope from weights. From weights to detection. So that this polytope will be isomorphic to polytope constructed from this kind of hyperplanes, half spaces defined by collection of integer vectors. This, let me call it capital B. So capital B would be a set of this. Yeah, let me call this B a set of integer vectors and a polytope B subscript B. So that's the statement. Is that that if we kind of construct this polytope from weights, then it will be the same as polytope for this vector B. So that kind of gives us a construction of kind of how to get a polytope picture from symplectic reduction. So let me give some examples, and then we will see how to get a kind of one collection of integer vectors, transfer one collection of integer vectors to another collection of integer vectors. Because for polytope, this relation is kind of easy, but for integer vectors, it is more complicated. So, but let me start with examples. So the simplest example would be to consider V1 as a symplectic quotient of V2 over diagonal U1 action. So we have like V1, V2 mapped into kind of rotation of V1 and rotation of V2 by the same phase. So it means that we have just one weight vector, which is two-dimensional vector. So this kind of vector WA and the vector, so it has the following components, so just 1 and 1. So W subscript 1 is 1 and W subscript 2 is 2. So now, because C2 is two-dimensional, so we will have two rows. So we have the following defining kind of equations for our polytope PW. So for PW, we need to impose that rho 1 and rho 2 are non-negative, and then we need to impose that rho 1 plus rho 2 equals to some mu. So that is WA, rho A in this case, so W1 and W2 are just 1. So that are kind of our defining equations for polytope, and let us just draw it okay, so let me draw this two-dimensional row plane. So then first we impose condition, so that will be like row 1 and that will be row 2. So first we impose these two conditions, that row 1 and row 2 is positive. So that gives us a restriction to kind of positive quadrant. And then we have this condition that rho 1 plus rho 2 equal to mu. And here we have several options. So let me start with mu positive. So if mu is positive, then this line defined by rho 1 plus rho 2 equals to mu intersects axis at the value mu. So that is this line rho 1 plus rho 2 equals to mu. And we are interested in this kind of condition. So we are only interested in a part of this line which lies in the side of positive quadrant. So therefore, as a result, our polytope PW, basic polytope, is essentially a kind of an interval that is cut out from these equations, like two inequalities and one hyperplane equality. So then, if we change mu, say if mu is kind of exactly 0, so then as a solution we have just single point, and in the worst case scenario, when say mu is negative, so then let me say that here the mu is just that PW is just empty, so there are no common intersection points. So in this orange case, PW is just a single point, which is a point at the origin. And for positive mu, kind of PW is an interval. And indeed, if we analyze kind of moment map, we will see that the images of a moment map, which is absolute value of W1, absolute value of Z1 square plus absolute value of Z2 square. So the image of a moment map kind of only covers positive mu. So therefore, in kind of by taking a pre-image, we should take a pre-image of a valid value of a moment map. So mu better be non-negative. And then mu equals 0 is this kind of special points in these values of the moment map. So moment map take the kind of image of the moment map is essentially semi-interval R plus. So it can take all values from 0 to any positive number, and this kind of point 0 is kind of boundary point of these values, and it is not a regular point on a moment map. So okay, so therefore, if you take symplectic reduction of a regular point, then we will get like this unique PW, which is interval, and this interval is kind of very same interval that we got when we described CP1 as a collection of orbits. So we have 0-dimensional orbits and 1-dimensional orbits. And we can kind of similarly analyze other type of symplectic reduction. So all we need to do, we need to kind of construct a polytope that is given by certain inequalities and some number of linear equations. So maybe one other quick example. So if you take a P2, it's kind of symplectic motion of C3 by U1 squared. So then, kind of what we will get a kind of three-dimensional roll space. So roll space would be three-dimensional, and kind of the positive. Now we need to take a positive octant. So it's kind of 1/8 of the space where all rolls are positive. Like roll 1, roll 2, and roll 3. Yeah. So positive. And then we need to impose one additional equation. That row 1 plus row 2 plus row 3 equals some positive mu. And this equation will kind of cut out a triangle. So that will be like a plane that is cutting this angle, and the intersection of this hyperplane with this positive octant will be a certain triangle, and so in this case my W will be some triangle. And some kind of more careful analysis shows that this triangle is the same as this kind of polytope for P2, which is a standard triangle for P2. Is a standard triangle, so it is essentially a kind of polytope for C square, which is the semi-infinite polytope, which is just positive sector in a plane, and then we kind of compactify C square by adding another CP1. So in order to get CP1, we need to kind of compactify C squared by CP1. So that means that we essentially added this additional CP1 here and completing this picture of semi-infinite polytope into a finite polytope in a sense of a standard two-dimensional simplex. So here BB two-dimensional simplex. Okay, so that's kind of a way how you go from one picture to another picture geometrically. So then to get a kind of algebraic relation between combinatorial data, you need to do the following thing. So first, like the polytopes that we will get by this construction, so this B is kind of a set consisting of some finite number of this integer valued vector. So the size of this exactly in process. So that's what we get if you kind of carefully analyze the properties of the intersection. So therefore we have kind of in PV description, we have a matrix that is n times n plus s matrix, and in EW description, the weight matrix was a matrix which was like n times n plus s times s. So that was kind of weight. So that was like s vectors in n plus s dimensional space. And here we have kind of n plus s vectors in n dimensional space. They are vectors E, alpha, and these are weights. Okay, that will go. Okay, let's call it VA W alpha. So then what we can do, we see that they kind of have, if you write this weight vectors and normal vectors into matrices, so then these two matrices will have kind of one common size, and having one common size means that we can multiply them. So let me specifically add indices. So W has like upper index A, which runs over n plus s and the alpha. So similarly B. Okay, so the number of vectors is n plus s, so I can label them with the same capital A, and they are vectors in n-dimensional space. So their components I can label with little a. So little a runs from 1 to n, capital A runs from 1 to n plus s, and alpha runs from 1 to 12. So then the way to go from kind of one data to another data. So given this W A alpha, we can do the following. So we can consider a kind of collection of equations. So we can look at this set of linear equations. So there will be like S equations, and then so it's S equations. And this S equations in n plus S dimensional space. So this, so that's equations in n plus S dimensional space. So given that the matrix is kind of full rank, that implies that we have kind of n solutions or n-dimensional solution space. So kind of all b's that are solved this equation. So all these vectors b understood as a vectors in n plus n s dimensional space. So all these vectors ba. So they belong to some n-dimensional space of solution. And let us kind of choose integer basis in this n-dimensional space and denote this integer basis v1 to the n. And that would be precisely our kind of normal vectors for a polygon. So normal vectors. So we got them by kind of looking at kind of integer basis for a solution to this S linear equations in S plus S dimensional space. So we get exactly n independent solutions, and then we kind of look at these solutions instead of n vectors in n plus S dimensional space. We can look at them as n plus S vectors in n dimension. Okay, so we essentially transpose this matrix to think of certain number of vectors in different. And then similarly, we can given these vectors b, we can once again also kind of consider this set of equations. So it's once again equations will be in n plus S dimensional space, but now there will be n equations in n plus S dimensional space. And once again, given that we are dealing with a matrix of a full rank, this metric defined by B is a full rank, so generally it would mean that we have some S-dimensional linear space of solutions. And we choose some integer basis in this space, so this W A integer basis. And that would give us back kind of weights of the recursion. So going into one direction, so for kind of polytope construction, so this kind of weights, they essentially define everything. So there is no kind of additional data. So given the weights, we kind of solve for these vectors, and given the vectors, we just draw a polytope by intersecting the corresponding kind of half spaces corresponding to this vector. However, if you want to go in opposite direction, so if you are given a kind of polytope which is intersection of half spaces for a given collection of primitive integer vectors b, so we get some weights w, but the weights w Okay. So weights W in the toric construction they also define everything. So the only kind of potential property is kind of to get GIT construction from these weights. But I think since we are not going to use GIT construction, so maybe I'll just skip that part for sake of saving time. So I will still add it to my lecture notes, and I will kind of send you updated lecture notes sometime later this week. So for kind of GIT quotient, so for GIT quotient we need to kind of subtract something from C n plus S to perform the quotient of the system to them. And there is a certain also geometric construction of how to get this B of this extra variety that we need to subtract from n plus S before the quotient. So how to relate this B to these vectors B, and how vectors B and then the polyton. How to get Z from just the polyton construction. But since we're not going to use GIT quotient anywhere in our course, so I will just leave it as some kind of home reading if you are interested. So for us, kind of prime thing is that in some applications we're going to need the symplectic quotient construction. So, but for most of the applications, we will just deal with this polyton construction for toric variety. So that's why all kind of you need to remember that essentially kind of this B and W, they are like roughly orthogonal to each other. So they satisfy this kind of conditions that properly packaged vectors B and properly packages weights W, they're kind of orthogonal to each other in n plus S dimensional space. Okay, so now let's see what we do this time. 11:45. Yeah, I think now it's actually a good time to make another short break, and after the break we will talk about one more thing. So remember when we started talking about Gromov-Eaton invariance, which was kind of a side of a mirror, we mentioned that the Gromov-Eaton invariance, they're essentially like generalization of intersection theory on our variety. That's the simplest Gromov-Eaton invariant, like degree 0, genus 0, was essentially just intersection of cycles on our X. So therefore, for these toric varieties, it would be interesting to see like how to get a certain handle on kind of cohomology groups, because that was our observables in Gromov-Eaton theory. So how to describe cohomologies in terms of this combinatorial data, and then how to get like sort of product structure on cohomologies also in terms of combinatorial. So that would be our topic for after the break. And now it's 11:46. So let's make 9-minute break. Till 11:55, and then we will return and talk about cohomologies in terms of combinatorial. I have a question for you. So have you seen my message like yesterday? So yes. So I talked to Andrei yesterday. So he came and he said that because Louis is away today, so if you are interested, you can kind of talk to us in kind of unusual time of Louis, which is like 2:30 today. But once again, if you are free at that time, so.
Yes, I'm free.
Okay, so then let us meet at 2:30 today, because for Wednesday Andrei doesn't know whether he give a talk or not. So let's kind of not rely on that and try to talk at 2:30. Okay, good. Okay, so let's proceed to a third part of our today's discussion of toric varieties. So let me reset. So far we discussed two kinds of constructions for toric varieties, and discussed how to relate combinatorial data, like weight vectors and some weight vectors of the one action for risk reduction and primitive integer vectors for polytope construction. And now, in preparation to Gromov fitting theory, on story text, so we look at the RAM cohomologies of X. Okay, so X are smooth, compact, so all the RAM cohomologies, they are kind of isomorphic to other type of cohomologies, so we just call them cohomology of X. And we will look at kind of triple intersections. So that is kind of simplest Gromov fit invariant. So if you have gamma A, gamma B, gamma C, so all these gammas, they kind of belong to some representatives of these cohomology classes. So we look at genus 0 and kind of degree 0 Gromov fit invariant on X. So that is given by this very simple formula. So we just need to multiply this. I think I should probably just gamma 1, gamma 2, gamma 3. So we take a wedge product of this gamma 1, gamma 2, gamma 3 and integrate it over X. So that is, and if you know like a product on cohomology, so that is the same as a kind of standard pairing between gamma 1 and gamma 2 wedge gamma 3. So that are just some triple intersection on cohomologies, and that is kind of ring structure on this H star of X. So what we want to understand how to get question, how to compute H star of X and kind of triple intersection on it. Triple intersection. Combinatorial data. Okay. So first step is to get cohomologies. So for that we will use some nice construction. So for H star, we follow in the Fulton book on toric geometry, and he has like some very nice construction how to get a kind of H star of X. So H star of X as a vector space means that that we should get just some dimensions of these subspaces of cohomologies of different degrees. essentially what we get from Fulton's construction, we will get what is called Betti numbers, which are dimensions of case cohomology Betti numbers. So kind of we can package these Betti numbers into what is called Poincare polynomial. So it's kind of Poincare polynomial for x. It's just a polynomial of a single variable that is constructed in a very simple way. So we take a summation from k to real dimension of x, and here we use Betti numbers as coefficients of this polynomial. So beta k multiplies e to the power k. So that is probably something familiar to you. So because we are dealing with a complex manifold, so if you have complex dimensions, so then it's summation from k to n. So now kind of theorem that so for x given by a polytope, say polytope in this kind of with a collection of as I kind of claim it, these two polytopes are isomorphic. So given x constructed from a polytope and n is complex dimension of it. So then kind of Poincare polynomial px of t is given by the following formula. So the summation a goes from 0 okay. Sorry. This is some points. Okay, I think going from 0 to n, and here will be pk t squared minus 1 to the power k, and this pk is kind of number of faces codimension k faces number no, sorry, not codimension k. I think it should be k dimensional faces. So faces of our polytope P, it has faces of different dimensions, and here we also assume x compact. So x is kind of compact, constructed from a polytope, has complex dimension n, and then for this polytope P, we count a number of k-dimensional faces. We get this numbers pk. So then we substitute these numbers pk into this formula, and because here it's like t squared minus 1 to the power k, so we will get a kind of degree 2n polynomial. And because faces can go up to total dimension of p, so therefore this pk go from p0 to pn, and therefore the maximal degree of this polynomial is that k equals to n, so it's degree to n polynomial. And our Poincare polynomial, because x is to n has real dimension to n, it's also degree to n polynomial. So that is kind of very useful theorem. So it allows us to get from kind of counting faces of polytope to computing Poincare polynomial. So let me kind of just outline. So for details of the proof, I kind of refer you to Fulton's book, but let me just kind of outline or give you idea of the proof. Because it kind of uses some useful construction which is I found interesting. Other mathematics is about feeling and all things. So I kind of found this construction kind of rather nice and potentially useful for other applications. So what Fulton did in his book, so he kind of started with kind of definition. So he defined kind of virtual Poincare polynomial. And for virtual Poincare polynomial, so it has the following properties. So he still calls it x of t, and if x is smooth and compact, so then this px of t equals to kind of usual Poincare polynomial. Yeah. Now. Okay. Let me call this with var. So this virtual Poincare polynomial became real Poincare polynomial. So this idea of virtual Poincare polynomial is kind of extended Poincare polynomial away from this smooth and compact case, and to describe an extension. So he gave the following properties. So for other axes, of x defined by properties, and here he defined it in the following way. So if kind of y is closed algebraic subset of x, and u is just kind of x minus y. So then the x of t is the sum of y of t plus u of t. So if we cut kind of a subspace from x, so then kind of the polynomial, the virtual polynomial on x is just a sum of virtual polynomials for this kind of part that we cut it and the remainder. So then there are some other properties. I think not all of them are kind of independent. So some of them can be derived from other parts. So that's why kind of I will list them because I will use some of them. So they are not all independent. So he has some lemma that kind of derives some of the properties from others, not all independent. So in the sense that you can define it given a smaller subset of properties, but I want to kind of define it with a bigger set to make my life easier. So so if my x is kind of union of finitely many closed subvarieties, so then the x of t is just sum. Well, I think this one is probably kind of can be proven from a first one. So for a third one, maybe it's still derivable from a first one, but just write it in the following way. So suppose I have my variety x, which is Cartesian product of some y times z. So for Poincare polynomial, like when we perform Cartesian product, Poincare polynomials multiply, and these virtual Poincare polynomials they also have this this property that Poincare polynomial for Cartesian product is virtual Poincare polynomial for Cartesian product is a product of virtual polynomial. Okay.
Union means how to union it.
So I think it's disjoint union. Sorry.
You mean disjoint means this is isomorphism in this is isomorphism as the variety, or this just stratification.
I think it's like union of orbits. So okay, so it's not quite disjoint union, but
so xk is like
so
locally closed subvariety.
yes. So it's okay. I'm not sure how to properly close subvarieties. Next, so
Subvariety.
Okay, sorry, there. Okay, let me say it this way. Like, so we are going to apply to toric X. So it's like union of star to the power n orbits. So that's the only case which I need to apply. So in this sense, I think they are all kind of isomorphic to some C star to some power, and then kind of they gluing it over orbits of smaller codimension.
And they are disjoint.
Yeah, I think as orbits of different dimensions, they bound to be disjoint, because kind of the, say, zero-dimensional orbit does not belong to one-dimensional orbit. So they are disjoint.
So you mean xk is a single orbit?
Yes. So xk is a kind of single orbit, so this kind of union will have different orbits. Okay, so now what we can do to actually prove this theorem using this virtual Poincare polynomial. So theorem proof. So as kind of step one, okay. So our kind of key idea is to use like this property 2 and defining property. So for compact X, so Poincare polynomial of X by definition is this virtual Poincare polynomial. So now kind of X given from polytope means that X is kind of union of toric orbits Xk, and then we use property 2 to get here summation of these virtual Poincare polynomials for different orbits. So different orbits, so all this kind of xk, so they are isomorphic to some star to some nk. So they are all orbits of a certain dimension, and furthermore we have this relation between kind of faces of a polytope and orbits of a different dimension. So for each k-dimensional face, we have exactly one k-dimensional orbit. So therefore, I can use kind of a structure of my polytope to rewrite it in the following way. So it will be a summation, and we will have orbits from dimension 0 to highest dimension n, because our toric variety always contains c star to the power n as its orbit. So, and here will be exactly number of orbits of dimension k, and here would be virtual polynomial for a k-dimensional orbit, and this k-dimensional orbit we can denote as c star to the power 2. So we are kind of getting close. So we are getting relation between Poincare polynomial and virtual Poincare polynomial for k-dimensional orbit. So now what we left to do is to compute this p of c star to the power k, and here once again I can use a property 3. So because it is Cartesian product of k orbit, so therefore here will be summation k equal to 0 to n pk, and here will be virtual Poincare polynomial for just one dimensional orbit raised to the power k. Okay, so we are getting very close. So we reproduce it like sum from k to 0. We reproduce number of k-dimensional orbits, and here we even reproduced some case power of k square minus 1. So what remains to prove is to compute virtual polynomials for t star, and for that we can kind of cut. We can take some compact variety. So we know that virtual Poincare polynomial for compact variety matches with Poincare polynomial for compact variety. So let us take Poincare polynomial for CP1. So Poincare polynomial for CP1. So CP1 has only H0 and H2, and both of them are one-dimensional. 1 plus 2. And kind of by this construction, we know that the CP1 has this kind of polytope for CP1, which consists of one-dimensional orbits and two zero-dimensional orbits. So that will be like P star of T that we are trying to find, and then we need to add a contribution from zero-dimensional orbit, but zero-dimensional orbit is just points. So points, they are okay, smooth, compact toric variety. So each point contributes to Poincare polynomial by just one. So for a point, you only have H0, so no others. So therefore, from this equality, we can solve for P of C star. So it's 1 plus T square minus 2. That is precisely T square minus 1. And now we kind of get a complete proof of the theorem that kind of dimensions of homologies packages in Poincare polynomial given by this simple formula. So let me kind of make two important remarks about this formula. So for remark 1, so by definition of Poincare polynomial, so in Poincare polynomial, so all coefficients are positive. Because all coefficients are dimensions of some vector space, so they are positive numbers. However, here, like if we raise t square minus 1 to the power k, we will get like some possibly negative contributions. But t square minus 1 to the power k has negative contributions. So in a sense that they give us kind of polynomial terms with a negative coefficient. So the kind of non-trivial thing is that the fact that these pk's, they are number of faces for polytope, is kind of gives some additional constraint that removes all this negative contribution. That any time you kind of sum up these expressions, you will get a polynomial with positive contribution. So that's a kind of interesting remark 1. So just to kind of further illustrate remark 1, let me do one kind of computation. let me do a couple of examples to see how these negative coefficients cancel out. Okay, still better. So let me take x as a P2. So for P2, we kind of computed polytope today, and the polytope was so P2 was x for a standard simplex, standard two-dimensional simplex. So for standard two-dimensional simplex, so what kind of faces do we have? So we have kind of single two-dimensional face, so P2 is 1. So then for three-dimensional faces, for one-dimensional faces, so for one-dimensional faces we have three one-dimensional faces, and similarly for zero-dimensional faces, we also have three zero-dimensional faces. So let us use our formula to compute one polynomial for P2. So here we take three zero-dimensional faces 3 times 1. So then we have three one-dimensional faces 3 times t squared minus 1. And then we have one two-dimensional face. So it's 1 times t squared minus 1 squared. So it is 3 plus 3t squared minus 3 plus t to the fourth minus 2t squared plus 1. So we see kind of bunch of potentially problematic negative terms, but all of them kind of get overrun by appearance of similar terms with a similar t degree from other contributions. So this 3 cancel out, and here this 3 cancel out with the 2t squared, and we got t to the fourth plus t squared plus 1, which is familiar Poincare polynomial for P2. So P2 has only one-dimensional cohomologies in even degrees. Okay, so that's kind of an example how this cancellation works. So let me make another remark too. Or maybe not a remark too, because it's not something that we ignore, but we're going to use it. So let me call it corollary. So that is corollary that we're going to use a lot in our tropical construction. It's also important for Gromov-Itten theory, because in the Gromov-Itten theory, we have a kind of very special role for two-dimensional homologies, because they define like this class of the curve, or they define the degree. So the dimension of H2 roughly defines like the dimension of this degree vector. So let us try to get a kind of beta 2 of x. So which is second Betti number. Second Betti. Okay. I want second. Second homology is paired with second cohomology. I think it's fine. Okay. So our space is a compact space. So it's dimension of H2. But because the space is a compact space, so Poincare duality basically tells that it's beta 2n minus 2 of x. And it turns out that it is easier to kind of track this thing, and this thing is kind of Poincare polynomial of x, and we are looking at the term as a coefficient in front of t to the power 2n minus 1. 2n minus 2. So that is kind of easier to track because in our sum, kind of the orbits of of higher dimension, they come with a higher power of t. So that's why if you're interested in a power of t which is 2n minus 2, so then the only way to get to n minus 2 is to either have n-dimensional or n minus dimensional orbits. So for correct polynomial of x to n minus 2 comes from two contributions. So we say that Pn is square minus 1 to the power n, and here we are looking at the term to n minus 2 of degree to n minus 2, or it can be contribution from Pn minus 1 to t square minus 1 to the power n minus 1, also t to n minus 2. So it's easy to get a degree to n minus 2 from this term. So from this term, the coefficient in front of to n minus 2 is just p to n minus 1. So here we need to kind of apply some binomial formula and to get a coefficient to n minus 2. So it's actually minus n, because we raise 12th degree, times pn. So therefore what we get e n minus 1 minus n pn. Okay, and now so what we know the following thing. So kind of by assumption, which I think I haven't phrased. So we always assume that the text is connected. So it means that it has only a single orbit of the highest dimension. So it means that n is 1. So it's a single orbit of C star, the complex dimension of x.
In definition of toric variety, this must be true.
Yeah, so we can, yeah, I think in the definition we assume that it contains C star to the power n as a proper subset. Yeah, so it kind of, yeah, secretly assumes that it is connected. Okay, so we don't even need additional assumptions connected, so we just false switch. Okay, good point. So that is from definition. And then what about Pn minus 1? So Pn minus 1 is number of n minus 1 dimensional faces. But this n minus 1 dimensional faces for polytope, which is intersection of half spaces. So the number of these spaces is precisely a kind of a number of these vectors B. So we denoted this capital B as the set of this primitive integer vector B1 to BB, and this kind of B is continuity of this set. So therefore we get this kind of nice formula that beta 2x is given by the following thing. So it is kind of number of these half spaces that we use to compactify it minus complex dimension of x. So the second homology of x is kind of a difference between number of compactifying hyperplanes minus dimension of x. So in particular, I think if you look at another example, which is P2 of P1 cross P1. So P1 cross P1, we know that okay. So if you happens to do a homework or for some other reason, you know that P1 cross P1 has two-dimensional homology. So the degree of the map to P1 cross P1 is a pair of integer one. So for P1 cross P1, the kind of the corresponding polytope is just a square, and this square drawn in two-dimensional space. So it has it is constructed as an intersection of four half spaces. So therefore this cardinality of B is 4, and kind of dimension, complex dimensional space is 2. So that gives a correct beta 2. And this formula we will meet it it later when we will talk about tropical. So now in remaining 1 minute, let me just kind of give you a kind of a formula, which is a kind of very famous formula for this triple intersection. I will give kind of without derivation. We are okay. So since I'm moving slowly than I anticipated, so most likely we are not going to get to descendant invariance. So that formula was kind of a preparation to kind of see to a preparation for some like Giventhal formulas for descendant invariance, and kind of since I'm not sure whether I will get to descendant invariance, so let me just give you this formula so you have an idea of kind of how to compute these triple intersections, but I'm not going to give details because I'm not going to use it. Okay, so the key idea is existence of what is called Kirwan map. So which is mapped between cohomologies of symplectic reduction. So we have some kind of symplectic reduction of G action on M. So cohomologies of this space. So they are related to equivariant to G equivariant cohomologies on this M. That's like G equivariant cohomologies. On M. So given and this map is called K or kappa. Okay, so it's map K for K1, and then it's kind of key result. Is that map K is subjective. So it means that given kind of form here, alpha in these cohomologies, so we can construct a kind of preimage K minus 1 of alpha. Preimage exists, but so for all alpha, preimage exists, but may be non-unique. So it means that we can kind of describe the cohomology of symplectic quotient as a certain kind of classes in equivariant cohomologies of M. And because our group G is just a abelian group, so equivariant cohomologies of M, they are very simple, so it's just cohomology of M with coefficients in kind of polynomial of S variables. I think I will call them phi1 to phi. And then, so that's kind of one key result. So that is another extra simplification property that for this U1 group, this equivariant cohomologies, they have very simple description. And the third result is that using this map, we can map triple intersection, alpha 1, alpha 2, alpha 3, integrated over symplectic quotient G. So we can uplift this thing to primitives. And here perform some kind of equivariant integration over M. And it turns out that here, because this kind of equivariant cogomologies are kind of cogomologies with some polynomial with coefficients in polynomial ring. So for every kind of cogomology class alpha here, so we can, for k minus 1 of alpha, so we can find a representative that is just kind of degree 0 form, so just a constant, but some polynomial of pi. So so that is also always possible, and therefore here we can express this triple intersection understood as equivariant integration of m as some integration, as some residue integration for these three polynomials p1, p2, p3 constructed from kind of applying this inverse of Kirwan map. And this final formula and the integration goes over d phi 1 to d phi x. So, and this formula is kind of a generalization of our. Yeah, I think I'm not sure whether I talked about like for P1 for Pn case for x equals Pn. Okay, I think we talked that kind of cogomology ring is kind of isomorphic to this very simple ring that we take a polynomial of single variable and just mold it by a relation that Pn plus 1 equals to 0. Sorry, phi n plus 1 equals to 0. So that means that we have like classes 1 phi square and phi to the power n, and multiplication. This is multiplication with polynomial ring. So kind of when we talked about Jacobian rings, we said that kind of multiplication in a quotient in a ring that is some ring of holomorphic function quotient by some gradient ideal can be described in terms of residue formula. So we just P1, P2, and here we had like W prime, and we can pretend that is our W prime because that is gradient ideal in one-dimensional case. So therefore, following our logic from Gromov-Witten theory, we can rewrite kind of elements in this ring in this form and kind of triple pairing. So if we kind of compose a pairing with multiplication in kind of polynomial ring, so we will get this kind of 3-point function or triple intersection or kind of structure constants with index raised by a metric from a pairing. So we get this kind of formula that sort of triple intersection in this cogomology ring is given by this residue formula where we take product of three polynomials, divide by phi n plus 1 and take a residue at 0. So that is kind of small contour around 0. Small s1 around 0. And this kind of application of Kirwan map and this.
Excuse me, what is the definition for this capital D?
Yeah, so that's where I'm going. So capital D is some polynomial and it's constructed in the following way. So if okay, let me so this capital D, which is denominator, is given by a following formula. So suppose my toric variety is given in terms of symplectic reduction with some double. So what I do, I take my weights. I think it has upper index A, so that is coordinate on which it acts, and has index alpha. So alpha labels different U1 subgroups. So for each U1 subgroup, we have own coordinate phi. So this alpha runs here. So alpha runs from 1 to f. So we kind of construct for each coordinate, we construct this linear combination of weight multiplied by corresponding equivariant parameter, and then we take a product over all kind of coordinates from 1 to n+. Okay, and here I kind of missed a little bit. So here, in principle, I should write down some additional term that depends on this parameters mu alpha, because when we constructed toric variety by symplectic quotient, we need to take like j minus 1 of mu, and this mu is kind of also enters this residue form. But I think for regular value mu, I think the answer is independent on mu. So
this integral is what integral is equivariant?
So that is no. So this is equivariant integral, and that is all the ordinary kind of residue integral or residue at multi-dimensional residue at phi equals 0. Phi 1, phi 2, phi n equals 0.
So, sorry, this P is homologic value.
No. So these P are just polynomials of phi. So first we say that equivariant cohomologies are cohomology of m valued in polynomials of phi. And then for equivariant cohomologies, you can always find like representative that is just pure
This
polynomial of
notation
phi.
means phi 1 and phi s, they belongs to H star m.
No. So that is extension. So it's kind of cohomology of m. So that are forms valued in polynomial ring. So it's a linear combination of differential forms.
Polynomial, their coefficients are in H star m.
Yes, but we can always kind of choose a representative in cohomology class whose coefficient is just constant in H star of m. So that is at least I think holds for this equivariant cohomology feasibility.
Because here you see this H star x itself is a
it's as a ring. As a ring,
Yeah.
it's isomorphic to this one.
so it contains some torsion, something like. So this H star m here, if we understand it like this H star x.
Okay, so maybe here I should choose different variable to avoid confusion. So
So when we do this like residue integration, this P1, P2, P3, they are omega.
they are polynomials of phi. So these p's are kind of polynomials of phi.
Yeah, but their coefficients are some
No.
polynomial.
So their coefficients are complex numbers.
No. But here H star x is not complex number.
Yeah, so that's why here it's omega. So here it's not phi. So once again, when you have equivariant parameters, you can assign to them some degrees, because your differential in kind of equivariant cohomologies. So it has the following structure. So it's gram differential, and here it's equivariant parameter times substitution of a vector field that is generated by the symmetry. So here, this one, it has kind of cohomological degree +1. So it increases degree of form by 1. So that substitution of a vector field, it has cohomological degree -1. So it decreases degree of form by 1. So that's why the cohomological degree of phi need to be assigned by 2. So that's why here, if I have, say, polynomial which is phi 1 square, so in equivariant cohomology, so this would be equivalent to some form whose degree is 4. So this is kind of equivalent in equivariant cohomologies. so therefore, when I have just polynomial covariant parameters, they still kind of carry information about the original degree of the form. So kind of degree of the polynomial in equivariant parameters is kind of a degree of the form.
So sorry. When I think only in this case when M is a advanced space, the polynomial is not is a polynomial. In general, it's a cohomology value polynomial.
You say that I need additional property that the RAM cohomologies for complex spaces kind of trivial.
Yes.
So okay. Sorry. Yeah, maybe you're right. That here our okay. That M is En plus S and kind of cohomology of M. So there is only H0 and that is okay. Yeah, I think maybe you're right. So because I kind of used to think of the fact that I can always find representatives, but that's probably intuition only from complex space that I can always trade differential form into polynomials.
I'm still confused with if I know what is the polynomial P1, P2, and P3. This integral just the non-equivalent limit, just the constant term.
Yeah, so this is kind of equivariant integral, but this equivariant integral depends only on kind of cohomology classes here. And for cohomology classes, I can find like representative which is just kind of constant form times some power of phi. So kind of typical situation, like if I take let me kind of give you an example, but that example would be on P1. Okay, so suppose I'm looking at equivariant P1, equivariant cohomologies of P1. So I have like Fubini-Study form that was kind of ordinary cohomology on P1. So then, if I solve this equation that d phi omega equal to 0, I basically see that Fubini-Study doesn't close under this equivariant differential. So because there will be non-trivial part phi iv omega Fubini-Study, and this one is non-zero. But it turns out that even though it is not zero, it is actually d of something. And kind of closed form would be omega Fubini-Study plus phi multiplied by some function.
Sir, this is not a simple case. The P1 is not an affine space, and the equivalent cohomology is not a polynomial over the cohomology of each sum.
Okay, that's a bad example. Yeah, so I need to take here maybe take C. So if I let's try to redo it with C. So on C I have like my U1 action. So my vector field is something like d over d minus d bar d over d bar. So now so what I know that so suppose I have some kind of two form on C. So then this two form, because this cohomology is, so that is C of phi. So for any kind of two form, so this two form belongs to kind of differential form from C. This say coefficients in phi. So kind of phi dependence is trivial. But then I can turn this two form into some polynomial that corresponds to phi. And the way to do this is that I just doing what? yeah, let me kind of extend this form to a closed form under this equivariant differential. So so the closed combination would be something like dv bar plus phi multiplied by some function, and this function would be something like
I think it's very hard to consider equivariant Ram cohomology. Maybe we should consider equivariant singular cohomology in this case. Then the covariant map just the quotient, the phi.
yeah, but I think localization would work with any kind of cohomology.
Yeah.
So
That,
so I think even though like here the function that we would get is kind of bad looking function like growing at infinity like z squared, but in this equivariant integral I can always add some kind of e to the equivariant differential of something without changing the integral. So I can add like some kind of term that will kind of cut out this growth at infinity. So I can probably produce something like z squared from applying this equivariant differential to something. So in kind of equivariant sense, I can still integrate functions that are growing to infinity. So I think I can probably still do it with the Ram cohomology, but it will be harder. So, but as I say, I'm kind of, since I'm not going to use this in a course, I just wanted to give you some kind of overview of how to turn combinatorial data, which are this WA alpha that we discussed extensively last time and this time. So how to turn them into some kind of enumerative data, which is like intersection numbers of some cycles. So intersection numbers is some enumerative invariant of X. And it turned out that to kind of turn this combinatorial data into enumerative invariant, you need to construct like a certain polynomial from it, and then kind of use a residue formula with this polynomial as denominator. And that would give you some interesting integer numbers that are kind of.
I'm confused with how this combinatorial data simplify this integral. I mean, if I know what is P1, P2, P3, I have know what is this integral should be.
No, but like suppose you have just random, not random, but I'm giving you like some collection of weights. So first you need to compute your toric variety to compute intersection. I'm not sure what do you mean by knowing P1, P2, P3.
I mean, oh, maybe the application is the alpha 1, alpha 2, and alpha 3 is given by some combinatorial data.
No, I think here we can choose P1, P2, P3 as kind of any polynomial. So I think there is a way to kind of describe. Oh, okay. I'm not sure whether I can describe a polynomial ring as certain quotient. Maybe. Okay, that's I'm not sure. But I thought that here I can use kind of any basis in this polynomial. So I can choose like P1 to be like phi 1, P2, phi 2, and so on. So that will give me a kind of intersection on some classes. I don't know like which classes, but what I want to have like multiplication structure on my cohomology ring. So yes, I don't know how these classes look geometrically, but I know that kind of cohomology ring would be sort of isomorphic to some polynomial ring with this kind of multiplication and pairing structure. I'm not sure like how explicit it is, but for some kind of Gromov-Witten invariance with descendants, so we can kind of recover this formula as some special limit. So that was kind of my main reason for including it into course, because I planned to get to descendant invariance and to see these denominators appearing as from given Thales construction of some kind of 2-point functions or 2-point functions deformed by some observables. But now I'm not sure that I will reach there, so that's why let me leave it kind of sort of without good explanation and good proof, just kind of as a piece of knowledge that I personally find useful, but I agree that it's not. I didn't provide good arguments why it should be useful. So yeah, let me kind of treat this as very extensive remark that we can use this Kirwan map to compute some intersection of some classes which kind of not clear which classes. Okay, I think I'm already running like too much over time, so let's stop there. Okay. So,
This last example, when you say M is C, then this similarity quotient you want becomes.
no. So here it just was unrelated to symplectic quotient. So we just were trying to illustrate like how to go from differential form to polynomial of 5.
Yeah, that's right. I see.
Yeah. So that's why I took simplest example.
Okay.
Okay.